If I ask you to look at that diagram and tell me, without any discussion about continuity or discontinuity, identify where that graph is discontinuous, I bet you could tell me. In fact, I'm so sure of it that I'm going to ask you that question, and you're going to respond with your Yep. Okay. And I'm going to let you just do an open response, which means you can answer in a line. So separate your information with commas. Where's the comma on your Inspire? It's on there. I think it's on the left side. Okay. I'll go back to our question prompt here. So I just want you to identify where that graph is discontinuous. Continuous is there's something called the pencil definition of continuity. Are you familiar with that? What is it? So if I take my pen here and I'll put it in blue, okay, and I start drawing this, if I can continue to draw it without lifting the pen, it's continuous. When I get to the hole in the graph, can I continue to draw this without lifting the pen? No, I got to pick the pen up and continue on. When I get to this point, the same thing happens. I have to pick the pen up and continue on, and then I have this down here as well, where I have to pick the pen up and continue on. So there are three areas where it is discontinuous: C1, C2, and C3, because in neither of those, at neither one of those points, can I leave the pen down. Now, they're discontinuous for different reasons, though. And we're going to look at a definition of continuity so that we can, hang on a second, let me do this, make sure I say that like I promised you. Okay, there it is. So I want to make sure that we have the definition of continuity. And again, these three places are all discontinuous, but for slightly different reasons. Okay, so we have, let C be any number in the interval from A to B. Now, I don't know if you're familiar with interval notation or not. This interval notation, that's not a point. That is saying that we're going to let the input, so let's make that very clear. These are inputs here. This is an input interval. The inputs will range from A to B, and the parenthesis on each end means not including A or B. Open. It's the same way as saying A is less than X is less than B. It's the same thing. Okay, so if you're not familiar with that interval notation, it pops up every now and then. I try not to make a big deal of it, but it does come up, and I don't want you to be confused with it. Okay, so C is some value, some number in the input interval from A to B. F, be a function whose domain contains this interval. So the function F, now when we say the function F, we're talking which part of the function, input or output?
Output.
The output, yes. So the outputs of the function come from numbers that are in this interval from A to B. So if I have anything as an input between A and B, I will get an appropriate output of function F. Okay, the function F is continuous at point C if the following conditions are true. Number one, the function is defined at that value. Now, of these three situations here, we know C1, C2, and C3, it's not continuous. But of those, which one of those do we have that f of c is not defined? At C1, C2, or C3? At C2? I think it's defined. It might be hard to see, but that's a closed dot and that's an open dot. C1, yeah. So we would say that f of C1 is not defined because it has just an open dot there. Okay, the limit as x approaches c exists. The limit as x approaches c exists. Which of those other two can we say that the limit does not exist? Why at C2 does the limit not exist? Pardon? I can't hear you. Then lines don't matter. We can't clap. We have two different one-sided. Yes, absolutely. So we can say that the limit as x approaches C2 of the function does not exist because we have two different, I'm going to run out of room here, one-sided limits. Okay, so at C2 we know that that's the case. Okay, well, let's look at the third case. The limit of the function as x approaches c, the limit of the function is not the same as the function's value. Now, we only have one other choice, don't we? We've used C1 and C2, so let's think about what happens here at C3. What is the limit as x approaches C3? Now we have to make something up, don't we? Oh, let's make it up. Let's call it, what should we call that? D. And we'll call this up here, let's call that E. The limit of the function as the inputs approach C sub 3, what is the limit of the function? Is it down here or up there? The limit of the outputs as the inputs get closer and closer on both sides to C3. It must be down here, right? Okay, so the limit of the function as we approach C3 is D. What is f of C3? Yeah, it's way up there. Are D and E the same thing? No. So what we have then is that this case is true, that it is not continuous here because the limit of the function as we approach C3 is not the same as the actual function's value. So we have three ways then that we can have a function not continuous. I put all three on the same one. Okay, now, where's the function continuous? We know where it's not continuous, but where is it continuous? Any other places where it's not continuous? So again, to answer the question, where is it continuous, we answer the opposite one. Where is it not continuous? Well, it's not continuous at C1, C2, and C3. Is it not continuous anyplace else? It's okay every place else. Every place else it's okay from A to B. Every place else it's okay. So it's continuous everywhere except at those three places. It's important to know not just where the function is continuous, but where it's not continuous. So keep thinking of both of those. Okay, so now we have the task that we are needing to discuss this thing called continuity And in order to discuss continuity, part of our definition, in fact, 2/3 of it, involves the limit. That's why we had to have section 1.5, because we couldn't talk about this section until we knew what a limit was. Okay, let's go on. Determine whether the function is continuous on the entire real line. This question is the same thing as asking, where's the function continuous? Name all the places where the function is continuous. And that may be impossible to tell us where it's continuous. So you're going to instead answer the question, where is it not continuous? Okay? If I know where it's not continuous, then I can answer the question, because it's going to be continuous everywhere except at the point where it's not. So in order to do this problem, we're going to again think about, can we factor this denominator? If I can factor that denominator so that I have something go away that's going to be an impossibility, or if I can identify where the function will be impossible, undefined, that also is going to tell me where it's not continuous. So, how are you doing on factoring? What do we have? X minus 5 and x minus 1. Okay. So now that I know that I can factor that denominator, are there any values of that denominator that we can't use? Anything in the domain that we can't use? Yeah, x cannot be 5 and x cannot be 1. If those are the only places where it's discontinuous, then, undefined, then I'm close to understanding where it's discontinuous. So let's see here. The first question is, f of x is continuous everywhere, oops, there we go, except at these places. Oops, that's what's defined there. Okay. Except at. Okay. Second thing, if we look at, well, in fact, we don't even have to go any farther than this. The fact that we know that the function is not defined at two places, we know it has some discontinuities. Remember, one of the first things we do is the function defined? We know where it's not defined. So is there a possibility that this function is continuous everywhere? No. We are pretty much done at that point. Now, we can go through and look at graphing this. So I'm going to stop the recorder. I want you to go through and graph this, and let's just verify. What do you think is going to happen at x equals 5 and x equals 1? Continuous everywhere. So if it's a rational function, now what's a rational function? Well, if you've got a ratio, that means a fraction. It's going to be continuous everywhere that it has every number in its domain. And we just saw an example where we had one that, yes, it was continuous, except where where the function was not defined. Okay, describe the intervals in which the given function is continuous. Explain why the function is continuous on that interval, and if the function has a discontinuity, identify the conditions of continuity that are not satisfied. Okay. I'll let you kind of work on that on your own. Okay. I'm just going to walk you through this. F of x equals 1 divided by x squared minus 4. The first thing you ask yourself is, the function undefined for any input value. That's one of the questions. That's one of the first things you want to do. So we know that if it's a denominator, we got to be real careful, and you also might have already factored this. Again, there's no way to get rid of those denominators because there's nothing in the numerator to cancel with it. So is there any possibility for this function to be undefined? And we answer yes. For x equaling 2 and x equaling -2. So, therefore, f of x is not continuous, discontinuous, at x equaling 2 and x equaling -2. The fact that it is undefined means that it's not going to be continuous. Okay, and that's the first condition of continuity. Okay, has to be defined. If it's not defined, you can't do that. Let's look at another problem. We've seen quite a few. Let's do one more. X cubed minus 8 divided by x minus 2. Now this is where I don't know if you know the factoring of a perfect cube minus a perfect cube. You know, 8's 2 cubes, so it is possible there. I don't know if you know that or not. Take your inspires and let's see if you can do some factoring with that. It's nice to know if it can be factored. But, and it's not that hard to come up with the factors of it, but it's just maybe not something that you're familiar with. So, go to Menu, go to Algebra, go to Factor, and we're going to factor x cubed minus 8. And be sure you put comma x with respect to x. And that will give you that factorization. Should you know that? Yeah, maybe. We don't, usually do too much with factoring perfect cubes. So use your Inspire to help you out. Okay. Nicely, there is a factor of x minus 2. So I know that my numerator is x minus 2. My denominator has a factor of x minus 2. And the rest of that was x squared plus 2x plus 4. And I can cancel those factors. Now, does that mean then that the function is continuous? I've rewritten it. I've gotten it into something that doesn't have the denominator anymore. So is f of x still discontinuous at x equaling 2? Yeah. Okay. Okay. If it's not still defined there, is it a vertical asymptote? Isn't everything going to be a vertical asymptote for us? So take your inspires. And let's put another graphing page on. And we'll, I don't need to tell you guys how to do this, I don't suppose, but make sure that you have x cubed minus 8 divided by x minus 2. When we resolve this, when I say resolve, I mean when we take care of those factors that are in common, we get down to x squared plus 2x plus 4. Did you get a parabola on the graph?
Yeah.
Yeah. Why? Well, because it resolves down to the x cubed minus 8 divided by x minus 2 is the same function as x squared plus 2x plus 4 with one exception. So let's take your inspires and let's see what that exception is. We did not get the asymptote that we thought we were going to get. I'm going to put a point on, and I'm just going to put a point on somewhere on here. And we're going to, you know how to do this, right? We're going to change the input value to be what? Take one wild guess. Yeah. Go to menu and go to points and lines and do a point on. Okay. How do I change the value of this coefficient, or not coefficient, but this input value? For those of you who might need a little prompt, take the cursor and hover over it. Don't do anything else. Just hover over that input value. It will go to a shadow, fade it out. Hit enter twice. Hit enter twice and open up the text box. Backspace delete. What value do you want it to be? 2. What happens when you press enter? What happens? Did anyone get that to work? It cannot accept the change. Why on earth would it say that? After all, it's just a parabola, right? It's just a parabola. Why wouldn't it accept the change? Let me see who this might be. That's me. Okay. I'll just move me out of the way. Stay there then. Okay. Why wouldn't it take the value 2? It's undefined. Didn't we define f of x as x cubed minus 8 divided by x minus 2? So of course I can't put 2 in there. Even though the graph turns out to be a nice little parabola, it still is being defined by our original function. These are two functions that are identical except where? Okay, now before you answer that, let's try this. What I want you to do, because I can go through and do the same thing, and it says it won't take it. Let's go down and let's put in, we did this one other time, let's go down and put in the other function. What is the other, what did we resolve that to? Do you need some reminder about that? X squared plus 2x plus 4. Okay, we're going to put that in. So I'm going to type it as you type it, x squared plus 2x plus 4 and it appears to not have changed my function at all. If I move to that function, it says graph f5, which is where I put my, parabola. But remember, if it says tab, if you press tab, does it switch to graph of f4? I'm trying to get mine to stay there. So if I tab, it says graph of f4. Those are one and the same. Now, it would be interesting if we're on the graph of f4. Let's see if we can do that. If we're on the graph of f5. Let me try this again. I'm going to get over here, and I'm going to try something. I've never tried this before. I'm going to go to graph of f5. If I put a point on the graph of f5, will it go to 2?
Yeah.
It should, you know, it should, but does it? Again, I've never tried it like this, so let's see here. This would be pretty neat if it could distinguish between those two. Graph of F5. Okay, so I got a point there. If I take this point and I change that to 2, it goes. Now, why would that go on F5 and not on F4? Because on F5, it's defined, isn't it? If this is my F5 of X, and this is my F4 of X, 2 is defined on here, but it's not defined on F4. These functions are identical except at that one point. So back to our question, is f of x continuous? Now I want, whoops, back too far. I want to, let's see if I can do this or not. I want to go up here and I want to erase F5. Okay, so it's gone. And we know that we cannot take this point and put it at 2. How close to 2 do you think I can place this point? Can't put it at 2. I'm now back on my original function, but how close can I? Just give me a wild guess. 1 point. How many 9s do you have in there? Something like that? Okay. And sure enough, there it goes. It is there. But we know now that it's actually not on that graph because that is not a point on our graph. It can't be. It's undefined at 2. But we can pretend. So this is where we'd have to come up here and menu, actions. Have I shown you attributes? Attributes. Menu, actions, attributes. If I go to that point, I can open up another menu that if I use the left or right, I can put various types of icons there. And so I can put an open circle there that would indicate that it does not exist. It doesn't. It absolutely does not exist. So I need to be sure that if I'm communicating to someone about this problem, that if I'm going to show a graph of this, I better put an open circle there. Now, when it comes time for the quiz or test on this section, you may opt to use the very same features we have just gone over. If you don't want to, that's okay. You can draw it on the paper. But you have to put the open circle. Is this function continuous anywhere? Everywhere but there. Yeah, everywhere but there. Okay. We're going to say that f of x is continuous everywhere except where? X equals 2. Okay. Okay, let's go on to the next problem. Discuss the intervals on which the given function is continuous. Explain why the function is continuous on the interval. Now, we have what we call, this is a piecewise defined function. Why would we call it a piecewise defined function?
Because it has 2 parts to it.
Because the function is defined in pieces. Okay? The name tells it all. The function is defined in pieces. Yeah. How many pieces? two of them. Okay, two pieces. Let's look at the fact that this top piece is 3 plus x. What would the graph of that top piece look like? Nice straight line? Okay, it's linear. Nice straight line. What's the bottom piece going to look like? Parabola. Okay, good. Now, forget about, let's see if I can do this for us here. Where did that go? Forget about that piece over there. Individually, is 3 plus x continuous? Everywhere, right? It's polynomial. Okay? X squared plus 1, continuous? Everywhere. It's a polynomial. Okay. However, the line stops and the parabola stops, or starts, however you want to define that. And so we have the only place that this piecewise defined function could possibly, now the function is named, there's one function, but it's in pieces. So when we say the function is continuous, we mean that if I start with this function over here in the left side of the input axis and I travel of this function over to the left side, I'm doing it backwards, aren't I? The left side over to the right side, that I could do it without picking up my pencil. That's what we want to see. Not that is this piece or is this piece. We mean the whole thing. So let's take the inspires, because this is something that we don't practice very much of. And we're going to, let's do this. Go to, if you're on the black one, go to Document. If you're on the gray one, do a Control Home. Go down to Insert, and insert a new problem. I don't want to keep counting F6, F7. Okay, we'll just do a whole new problem here. So if you're on the gray one, Control Home. If you're on the black one, it's just Document, and we'll do a whole new problem. And we're going to do a graph problem here. So a graph page. Okay. I need a template for piecewise defined functions. Templates depends on your Inspire. If you're on the gray one, it's Control on the multiplication. If you're on the black one, it has its own button right there. The gray is Control multiplication. If you look at this, we have actually two choices. We have one that only has 2 pieces, and we have one where we could have multiple pieces. We only have 2, so we'll choose the one that has 2 pieces. And then press Enter. Okay. The first piece, let's see, that was 3 plus x, tab over, and we have that x is less than or equal to. Now, on the black one here, if you do Control on the equal sign, you get a little place where you can get a less than or equal to. On the gray one, I'm going to remind myself, on the gray one, it is, yeah, there's a couple ways you could do that. You can do Control less than. You can also do, I was looking at the Control on the booklet, and the book is over here. It's called the catalog, and that's a symbols palette, and you can then find a less than or equal to on that one. So let's see, I want to be less than or equal to 2, tab, and I have x squared plus 1, tab, and we have that x is greater than x is greater than 2. Okay, press enter. And we can see that something happens over here at 2. Now I'm going to just grab that screen. I'm just doing a grab and drag anywhere in the open space just to get more here. And I need to know what happens at 2. Now, analytically, remember our 3 conditions? Does f of 2 exist? Let's go back with our work. Number 1, well, let's just ask the question, does f of 2 exist? That's the first criteria. And so, you know, f of 2, which piece of this function am I allowed to use if I want to find f of 2? The top piece or the bottom piece? Because it's the only one that has the or equal to. So I have to put it in that top piece. So f of 2 is 3 plus 2 is 5. Does f of 2 exist? Yes. Check mark. It's done. Number 2. The limit as x approaches 2, the question is, does, I should put the word does that exist? Now, if it exists, remember, limits exist if they have the same value from the less than 2 side as they have from the greater than 2 side. So we've got a little bit of work to do here. To answer that, we have to say the limit as x approaches 2 from the less than 2 side. And then we have to look at the limit as x approaches 2 from the greater than 2 side. Which piece do I use for being less than 2? Top piece or bottom piece? Top piece. So this would be, it's just a polynomial, so I can use direct substitution, and it's 5. What about for the greater than 2 side? I'd have to come down. Okay. Again, it's a polynomial, so I can do this. I can use direct substitution. Does the limit exist? From both sides, we go to the same thing, and the answer is yes. Check mark, we're done. What's the third criteria for continuity? Say it again. Yeah. Does the limit as x approach 2 of the function have the same value as the function at 2? That's the question we have. Well, what's the limit as x approaches 2? 5. What's the function's value at 2? 5. Are those equal? Yes. So the third criteria. Is the function continuous at 2? Yeah. Therefore, put the therefore above here, therefore, f of x is continuous at 2. Is it continuous, though, everywhere? If you look at this, the line is continuous, the parabola is continuous. So if both pieces are continuous, the only place it could possibly break down is here at the joint, you might say, you know, at where they meet, and so it's continuous at 2 and everywhere. Okay, we're going to pick this back up. We'll talk more about finishing up section 1.6. The quiz is going to be the main thing. Please be prepared for that. See you all later. If the graph isn't obvious to us what it is, then we have to go to something analytical. And the analytical is using these the three conditions for continuity. So let's just go over and refresh our memory on that. One is that the output value has to be defined at that point. So we had an example here where we said at C1, the output value is not defined, it's obvious, maybe, to me at least, it's obvious that it's not continuous, because if I want to take my pen, and you can't see me doing this, I guess, if you go back to the video, but you can verify that I am going to make it obvious here. If I take my pen and I try to draw from here to here, I must lift my pen up and place it down on the other side to continue drawing. It's called the pencil definition. So if the graph is not obvious like this one, that is an open circle, then we can look at the function and see if the function value is defined. It's not, so therefore it's not continuous. If we look at C2, is the function value continuous? And it is, because there's a dot here. Okay. Now don't be mistaken, I'm not asking is it continuous through here. Oh, maybe I did. I'll have to rewind my own tape here and see what I did ask you. What I meant to say was, is the function value defined here? And the answer is yes. Is the function continuous here? The answer is no. It's defined because there's a dot. Then we go to the second piece of the definition. Is the limit? Does the limit exist? And because we're going to this value of output on the less than C2 side, and this value of output on the greater than C2 side, we do not have a limit. Or excuse me, we are not continuous here. Third criteria would occur with here, is the function value defined? And the answer is yes. Does the limit exist? And the answer is yes. But are they one and the same? And that's where it breaks down, that we have to say no. It is not continuous here, because although the function value is defined, the limit exists, they're not one and the same. So that's just the analytical part of what we're doing. Again, a lot of these graphs you can look at and just tell. Use your intuition. Intuition is good for us in many things in life. Why not in math? So intuitively you can see this is not continuous. But others are not quite as intuitive. Okay, so we went through a few examples. We know that polynomial functions are continuous everywhere, so if it's polynomial, you really don't have to go through those three conditions. Just tell me it's polynomial. I know it's continuous then. Okay, so we got down to then this piecewise defined. Now, the reason we need to talk about this piecewise is that it's like anything else. The weakest point in a structure is at a joint. So if the joint fails, then the whole thing's going to come down and collapse. So on this one, 3 plus x, just that alone. Nice polynomial function. What do you know about its continuity? Continuous everywhere. Okay. What about x squared plus 1? By itself, it's a nice polynomial function, continuous everywhere, but I can only use inputs less than or equal to 2 for this piece of the function, and I can only use inputs greater than 2 for this piece. So where's the weak point? Where's the possibility of being discontinuous? At 2. So we have to look at that and put it through its paces. Does f of 2 exist? And again, which piece can I use if we're using the input of 2? It's only the top part. This is a common error among math students. It's only the top part we can use because it's only here that we have or equal to. So the output value is 5. Does the limit exist? And the limit is approaching it from both directions. So if I approach it from values less than 2, which piece do I use? The linear or the quadratic? Yeah, I'm going to have to use the linear because this is the only place that we have values less than 2. And so if I do that, I can put, it's a linear, it's a polynomial, so I use direct substitution. As I approach it from the less than 2, I get 5. What about from the greater than 2 side? Well, the only piece I can use for values greater than 2 would be the quadratic. Use direct substitution, I get 5. If both of the one-sided limits are equal, what do you know about the limit as x approaches 2? Does it exist?
Yes.
And it is the same thing then as 2. Okay, so, or yeah, as 5 there. Okay, so then the third criteria is we've got the function value, we've got the limit. Are those one and the same? And this is where we would definitely need to use this because, again, it may be obvious on the Inspire, but it's, we don't have open holes that automatically get generated on the Inspire. So we look at those. The limit exists in is 5, the output value exists in is 5, and those are the same, so therefore, the function is continuous at 2 and at every place else too, because of the nature of each of these. Okay. So now we come to my new problem here. Describe the intervals on which the given function is continuous. Explain why the function is continuous on the interval, and if the function has a discontinuity, identify the conditions of continuity that are not satisfied. These are the 3 conditions we're talking about here. So I have that h of x is the composite function of f and g. I have f of x is 1 divided by the square root of x. I have g of x is x minus 1. Okay. If I am looking at h of x, and I know that it's f of g of x, what's another way I can write f of g of x? F of what? X minus 1. Why? Because the output of this function is g of x. That's why we can write it in here. The output of one function is the input of the other. But we can also, because the equal sign tells us so, we can also then use x minus 1 as the output of g of x, and that goes in here. So we have 1 divided by the square root of x minus 1. Now we have this criteria over here that says x is greater than 1. Why would that be necessary? Again? I don't get 0. Actually, so I don't, well, okay, so I don't get 0. I don't want 0 because it's undefined. But why is it greater than 1? I could have simply said that x does not equal 1, but this says, that would allow me to use other things like 0 and negative 1 and so forth. Yeah, I want real numbers only. If I have a 1/2, if x is 1/2, I'd have the square root of negative 1/2. I want to stay with the real numbers, so I'm going to stay with positive radicands in there. Okay, now, describe the intervals on which the given function is continuous. So the given function now is h of x. F of x and g of x were important to us in order to build h of x. But what interval would give us continuity on here? Erase that and start over again. That looks too sloppy to even put out there. Let's try it again. H of x is continuous for what input values? We kind of said it, didn't we? Yeah. For the inputs greater than 1. Other than that, we're going to have then some unreal numbers, and we can't plot non-real numbers on a coordinate plane of real numbers. So we don't have the ability to put those values in there, so we have to have that x is greater than 1. Okay. We could, if it has a discontinuity, identify the conditions of the continuity that are not satisfied. Well, let's see. Is there an h of 1? Does that exist? and that doesn't exist. So none exist. Okay. We can also say, well, what about the limit as x approaches 1? Again, we have to qualify this. We would have to qualify that we can only come to it from values greater than 1. And if we are coming to values greater than 1, what do you think is going to happen on this? If this is 1, and I approach this from values greater than 1. Pardon? I'm sorry, what was that again? I'm sorry, I just didn't hear you. Didn't mean you were wrong.
No, it's only one-sided.
It's only one-sided, yes. I can identify a one-sided limit here, and so you're right. The limit itself does not exist. What happens here? Does it just come up and stop? So we can say, well, what happens? Let's try this. What happens if suppose that x is equal to 1 1/10? What would that equal? So what would it be? 1/10, the square root of 1/10. Offhand, I don't know what the square root of 1/10 is. We could get some estimates there. We're going to turn to the Inspire in just a moment to see if we can help out. 1.01. So that'd be 1 divided by the square root of 1.1 1/100th minus 1. That would be the same as 1 divided by the square root of 1 100th. Now that we can do, can't we? The square root of 1 100th. What multiplied to itself gives you 100? 10. Okay. So this would be the same thing as 1/10. Well, what is 1 divided by 1/10? Multiply. Invert multiply. 10. Well, let's see. What else do we know for sure? What happens is, I don't know if anyone has this already imagined. I don't know if this is going to be a nice one to work on, but what is that? Tenths, hundreds, thousands, 10,000s? That should work. What's the square root of 1 1,000th? Tens, 100,000, 10,000, 1 10,000th. Or should it be 100,000s?
0.01.
0.01. In other words, 1 divided by 1 100th, what's that? 100. What's going to happen if I choose another appropriate number that has a perfect square to it? I don't know what this number is, but let's suppose that's it. Is the value going to be more or less than 100? So do you get the idea? What's going to happen to these output values? As we get closer and closer, what's going to happen? Okay, yeah. So the limit from that one side doesn't even exist. So we want to know, is the composite function continuous? Well, is it continuous until we get to 1? Would be a good question. Is there anything in our work that would indicate that as we take numbers farther and farther away from 0, that we would have anything that would be undefined? What if I put this to be 101? If x is 101, that would be 1 divided by the square root of 100. What's the square root of 100? So that would be 1/10. So if I'm out here at 101, my output is 1/10. If I had x to be 100,000, thank you very much.